Welcome back, everyone. Dr. Chem here, coming to you straight from the Materials Characterization Lab. Today, we're unlocking what is absolutely one of the most powerful analytical techniques in modern science, Powder X-Ray Diffraction, or PXRD for short. In this explainer, we are going to completely demystify PXRD. We're taking it all the way from the theoretical physics of wave interference right down to practical, hands-on laboratory applications. We're talking about identifying everything from pharmaceutical tablets and nanomaterials to unknown corrosion products. Get ready, because we are about to see the invisible internal structures of the very materials that build our world.
But hey, before we dive into the heavy machinery, I want you to ponder a seemingly impossible question. How on earth can we possibly measure distances smaller than a nanometer? To put that into perspective, we are talking about measuring the hidden, invisible, empty space between individual atoms in a solid crystal. I mean, we obviously can't just use a standard ruler, right? And even our most powerful optical microscopes are totally limited by the wavelength of visible light. We literally need a tool that is on the exact same scale as the thing we're trying to measure.
And honestly, that is exactly where X-rays save the day. If you think about the electromagnetic spectrum, visible light sits right there in the middle with wavelengths between, roughly 400 and 750 nanometers. But look way farther down at the X-ray region. X-rays are electromagnetic radiation with wavelengths between 1 picometer and 1 nanometer. Because their wavelength is literally on an atomic scale, X-rays are perfectly sized to act as our ultimate atomic ruler. They're small enough to slip right into a crystal lattice and interact with the actual planes of atoms themselves. It's kind of mind-blowing when you think about it.
So here's our roadmap for today's explainer. We'll quickly cover the principles of X-ray diffraction, break down Bragg's law, explore the PXRD instrument itself, talk about the absolutely crucial step of sample preparation, learn how to read a diffractogram, and wrap up with some advanced PXRD applications.
Okay, let's dive right into Section 1, the principles of X-ray diffraction. To kick things off, we really need to focus on the structures of the materials we're actually trying to measure. Because, spoiler alert, X-ray diffraction doesn't just work on anything you put in the machine.
The absolutely crucial distinction we have to make here is between crystalline and amorphous materials. For X-ray diffraction to even happen, the material absolutely must be crystalline, meaning its atoms are arranged in a highly ordered, repeating three-dimensional pattern with perfectly uniform spacing. Think of things like table salt, sodium chloride, or quartz. These atomic planes act exactly like a finely ruled diffraction grating for our X-ray beam. On the flip side, amorphous materials like glass or certain plastics, well, they're disordered. They completely lack that long-range periodic array. Because they don't have those nice uniformly spaced atomic planes, they simply cannot produce the sharp, distinct diffraction patterns we're looking for.
Which perfectly brings us to part 2, understanding Bragg's law. Now that we know we need a beautifully ordered crystal, let's look at the mathematical key that unlocks that atomic structure.
To really get Bragg's law, you first have to grasp the foundational physics behind the whole thing, and that's constructive interference. See, because X-rays are waves, when they bump into each other, they can either amplify each other or totally cancel each other out. If the waves are perfectly in phase, meaning their crests and troughs match up at the exact same time, they stack together, and boom. This produces a resultant wave with a much higher amplitude. This amplified signal is what we call constructive interference, and I can't stress this enough, it is the very basis of the diffraction signal we measure in the lab.
Notice how waves combining in phase naturally stack their crests to create a highly visible, powerful signal. But if waves combine 180 degrees out of phase, they completely cancel each other out. You get absolutely nothing. Zero irradiance. That's destructive interference. Now, inside a solid crystal, you have thousands of tiny atomic planes scattering X-rays all at once. We only see a signal when those scattered X-rays perfectly align in phase to constructively interfere.
So the real trick is knowing exactly when that constructive interference is going to happen, right? Well, that is entirely governed by Bragg's law. N lambda equals 2d sine theta. This elegant little equation, formulated by W.L. Bragg, is basically the golden rule. It determines the specific angles where coherent scattering will actually happen from a crystal lattice. Let's break down exactly what this means visually, because it's super cool once you see it in action. Think about the parallel planes of atoms inside our crystal, separated by a physical distance we'll call d. So X-ray number 1 hits the top layer and bounces off. Simple enough. But X-ray number 2? It has to travel deeper into the crystal to hit the second layer. That means it travels an extra distance. Specifically, that path segment A to B plus B to C. And thanks to some basic trigonometry, we know that extra path length equals 2d sine theta. Now here is the magic part.
For X-ray 1 and X-ray 2 to bounce back perfectly in phase, giving us that massive constructive interference we need, that extra path length absolutely must be equal to a whole number integer multiple of the X-ray's wavelength. That's the n lambda part. If the geometry is off even just a tiny bit, the waves destroy each other and we see absolutely nothing.
All right, let's move on to part 3, the PXRD instrument itself. We've got the wave physics down, we get the geometry. Now let's jump from the theory into the engineering reality. How do we actually pull this off in the lab?
The journey of an X-ray through a modern diffractometer basically happens in 4 main steps. First up, we generate electrons in a cathode ray tube by heating up a filament. Second, we take those electrons, accelerate them with some serious high voltage, and smash them into a target metal. In inorganic labs, this is typically copper. When those electrons slam into the copper, they knock out inner shell electrons, and the copper emits our characteristic X-rays. Third step, we filter and collimate those newly born X-rays into a tight, parallel beam and shoot it straight at our sample. And finally, step 4, we catch those scattered waves using a highly sensitive detector.
Following this journey, notice the vacuum chamber on the top left where our X-rays are born. See how the beam travels down, passes through a collimator to keep all the rays nice and parallel, and then strikes the sample, that pink area right in the middle, at an incident angle of theta. The diffracted beam then bounces off at that exact same angle, theta, meaning the total angle between our incoming beam and the detector is 2 theta. The detector then physically sweeps through different 2 theta angles to capture the entire diffraction pattern. It's an incredibly precise mechanical dance.
Now let's ground this in reality. Looking at an actual physical goniometer setup in the lab, you can clearly see the massive X-ray tube dower on the left. That's our beam generator. Right there in the dead center is the flat sample holder, where your tiny pile of powder sits. And over on the right, you've got the receiving slits leading right into the detector. This entire circular setup, the measuring circle, precisely maintains that strict geometric relationship between the X-ray target, your sample, and the detector while it scans.
But here is the catch, and this brings us to part 4, crucial sample preparation. All of this multi-million-dollar engineering is completely useless, literally a paperweight, if your sample prep is bad. This is universally acknowledged as the most critical and, honestly, the most error-prone step in the entire process.
Remember, we are talking about powder X-ray diffraction here. If we were doing single crystal diffraction, we'd just mount one perfect, highly ordered crystal. But for powder diffraction, we desperately need what's called an isotropic sample. That means we want a statistically infinite number of tiny, tiny crystallites, ideally less than 10 micrometers in size, and they need to be oriented completely 100% randomly. We want every single possible crystalline orientation to have an equal shot at facing the X-ray beam. That way, all the atomic planes get a chance to satisfy Bragg's law and diffract their signal. And honestly, achieving this usually comes down to good old-fashioned, tedious hand grinding with a mortar and pestle.
If you rush your grinding, you might fall victim to a fatal flaw we call preferred orientation. Imagine your sample doesn't break down into those nice, random, isotropic spherical grains we want. Instead, say it forms flat, microscopic plates or long, elongated needles. Well, when you go to pack those into your flat sample holder, they aren't going to sit randomly. They're naturally going to stack flat on top of each other, aligning with all their neighbors. This artificially blows up the diffraction signal from the flat planes and completely hides the planes standing on edge. It totally ruins your statistical data, so always grind your samples properly.
Okay, assuming our sample prep was flawless, let's move right into part 5, reading a diffractogram. What does this amazing detector actually spit out for us to look at? The detector gives us a diffractogram. On the horizontal x-axis, we've got our diffraction angle, which we measure in 2 theta, and on the vertical y-axis, we have the intensity, basically just the raw count of X-rays hitting our detector. Each one of those sharp, distinct spikes, that represents an exact angle where Bragg's law was perfectly satisfied and constructive interference occurred. These specific diffracted peak positions, combined with their relative intensities, act as a completely unique, highly specific fingerprint for that exact crystalline phase.
Decoding this fingerprint gives us just a massive wealth of physical data. The peak position on the x-axis directly tells us the distance between those atomic planes. This lets us identify the phase by checking it against a database, and we can even calculate the size and shape of the unit cell. The peak intensity tells us how much of that specific phase is present, and it even gives us hints about what kinds of atoms are actually arranged in those planes. And finally, if you see a broad, sweeping halo or a smeared bump hiding in the background instead of a sharp peak, that instantly tells you there's amorphous, non-crystalline material, like a glass or a polymer, sneaking around inside your sample.
Now, identifying basic materials is great, but PXRD is capable of so much more. Let's wrap up with Part 6, Advanced PXRD Applications, and see just how far we can push this technique.
Because PXRD is so incredibly sensitive to both sharp peaks and those amorphous halos we just talked about, we can easily calculate the exact percentage of crystallinity in a semicrystalline sample. We can even hook up a heater to the sample stage and track phase transitions in real time. For instance, we can literally watch the crystal symmetry of something like barium titanate shift as it heats up. In the pharmaceutical world, it's a total game changer for studying polymorphs. Those are different crystalline forms of the exact same drug molecule that might have completely different solubility rates once they're inside your body. It is heavily used in geology, nanotechnology, battery research, and even in forensics to identify completely unknown corrosion products. The applications are practically endless.
We've gone all the way from the theoretical waves of the electromagnetic spectrum to mapping the precise atomic-level fingerprints of the materials that make up our entire world. By simply bouncing light off evenly spaced planes, we can literally see the internal architecture of the solid universe. So I'm going to leave you with this one thought. If Bragg's law can map the hidden spaces between atoms so flawlessly, what incredible structural secrets might the very next diffractogram reveal about the advanced nanomaterials and catalysts that are building our future? Thanks so much for hanging out and exploring this with me today, and as always, keep that curiosity focused.